Hello there, my name is David Cater. In this video we're going to be looking at inductors in DC. This is going to be a multi-part video, so the very first thing we'll do is just take a look at the basics of the inductor and the formulas that affect it. Okay, just to review, an inductor is just simply a coil of wire that's going to be producing a magnetic field around it when current starts to flow. So the amount of that field is going to be dictated by the amount of current that's flowing through that circuit and the properties of the coil. All right, so what are the properties of the coil? Well, we want to measure the inductance of the coil, which is of course measured in henries. And the properties of the coil that affect the magnetic field, the strength of it, is going to be the number of turns squared around the core, the core's material and the permeability of the core, and then the area of the core, the cross-sectional area. All right. The length of the core is going to actually reduce the strength of the magnet, so we'll take this and put the length of the core down here. All right. So this is really the physical properties that affect an inductor: turns squared, permeability of the core, and the area of the core, all divided by the length of the core. All right. So you can easily see that we can adjust the strength of the magnet by adjusting any one of these properties, physical properties, and then we can also adjust the strength of the magnet by manipulating how much current will flow through it. Okay, so once current starts to flow through, we actually start to create an expanding magnetic field, and what happens is we have a self-induction, and the expanding magnetic field starts to interact with the coil itself, creating a counter EMF. And that counter EMF is going to be fighting the source. It's going to be the opposite polarity to the source. So we're going to want to know exactly what the formula for that is as well. Okay, so the counter EMF, which is the voltage produced by the coil when the magnetic field is expanding, the counter EMF is going to be equal to the negative value of inductance, the quality of the coil and the core, and we're going to multiply that by the rate of change of current over the rate of change of time. So why do we do that? Well, the inductance is going to be basically how it will behave with a magnetic field, and that's all the physical properties, but this change of current over the change of time is a very interesting thing. So if current is rising very quickly, that would mean the magnetic field is expanding very quickly, and we have a very high relative motion between the magnetic field and the inductor itself, and therefore we produce a much larger counter EMF. And the negative sign here is to indicate that it's in the opposite direction of the source, fighting the source, and essentially reducing the amount of current that's going to flow through it in AC, and basically elongate the amount of time it takes for current to reach max in DC. Okay, so that's the basics of the inductor. We're going to use these formulas a few times to sort of analyze how the circuits are working, and we'll get a much better understanding as to what's going on with an inductor. Okay, so we'll see you in the next video.